హలో స్టూడెంట్స్, గుడ్ మార్నింగ్. గత పార్ట్లో మనం థర్మోడైనమిక్స్ పార్ట్ 3లో మనం డిస్కస్ చేసుకున్నాం. స్థిర ఉష్ణోగ్రత ప్రక్రియ, సమోష్ణక ప్రక్రియ అంటే ఏంటి, వాటి నిర్వచనాలు, వాటి మధ్య ఉండే వ్యత్యాసాలన్నీ నేర్చుకున్నాం. వాట్ ఎవర్ వి లెర్న్డ్ ఇన్ ద ప్రీవియస్ పార్ట్స్, 0th law of thermodynamics, first law of thermodynamics, molar specificates, the relation among them, Cp minus Cv is equal to R, that equations. Then we'll discuss what is an isothermal process and important features, the work done in an isothermal process. Then we'll discuss what is an adiabatic process. What is an adiabatic process? Then distinguish between an isothermal and adiabatic process. ఈ పార్ట్ లో మనం adiabatic process, సమోష్ణక ప్రక్రియలో work done in an adiabatic process, work done in an adiabatic process, ADIA, adiabatic process, work done in an adiabatic process. Here సమోష్ణక ప్రక్రియలో జరిగిన పనికి సమీకరణం రాబట్టడానికి ప్రయత్నిద్దాం మనం. ఓకే, సో గెట్ బ్యాక్. As we already discussed in the previous part, what is an adiabatic process and important features. Let me highlight once again here the process in which the pressure and volume and also temperature change in a perfectly non-conducting container, so that heat is not allowed. Be careful, not allowed to exchange. Perfectly non-conducting container, it is not allowed to exchange between the system and surroundings, right? So it is relatively very quick process, right? Here, the Boyle's law does not hold good. Separate equation is called adiabatic equation. We already discussed in the previous part. PV power of gamma remains constant. This expression we already discussed in the previous part. Now, in this part, let us try to derive an equation for work done in an adiabatic process. Adiabatic process అంటే మనం ఆల్రెడీ చెప్పుకున్నాం. ఇక్కడ ఘన పరిమాణము, పీడనము, ఉష్ణోగ్రత కూడా మార్పు చెందుతుంది. In this process, let us try to derive the work done in an adiabatic process. For a small change in a volume, the work done by the system, this we already discussed while discussing the first law of thermodynamics, isn't it? First law of thermodynamics, heat supplied to the system is equal to the sum of the increase in the internal energy and the external work done by the system. Hope you remember this expression, heat supplied to the system, first law is utilized to increase the internal energy, du, plus the external work done. The external work done, this is PdV. This is first law of thermodynamics. Okay, for a small change in the volume, the work done is given by dW is P dV. Suppose the volume changes adiabatically, be careful, from V1 to V2, then total work done in adiabatic process is given by, on integrating the above expression between the limits V1 and V2. Here dW, small work done for a small change in the volume. So we'll just continue this. dW is given by P dV between the lower limit V1 and V2, isn't it? Now, what is an adiabatic relation? As we already know from adiabatic relation, this is PV power of gamma is K, constant. So constant, let us say. This we already discussed in the previous part. This we can write like this: P1 V1 power of gamma is equal to P2 V2 power of gamma is equal to K, constant. Here gamma ratio of two specific molar specific Cp by Cv, right? రెండు మోలార్ విశిష్టోష్ణుల నిష్పత్తి అన్నమాట గామా అనేది. So this the work done in an adiabatic process for a small change in the volume, the work done by the system, let's say is given by PdV. So if volume changes from V1 to V2, total work done is obtained on integrating the above expression with between appropriate limits, say V1 and V2. Now dW value, say equation 1, you substitute this value PdV. But adiabatic relation, as we already discussed in the previous part, adiabatic relation you already discussed. So substituting that value, adiabatic relation PV power of gamma is equal to K is a constant, or P1 V1 power of gamma is equal to P2 V2 power of gamma, that product remains constant. Now get back, substitute and simplify. So this expression, so from this expression adiabatic relation, P can be written as K divided by V power of gamma, isn't it? So now substitute and simplify further, so you'll get this expression. This is total work done. So here P is given by, since adiabatic relation PV power of gamma is equal to K, so that implies P is equal to K divided by V power of gamma. Be careful, this is V is the volume here, gamma is the ratio of specific heats. Okay, so now I'll continue this here, substituting the above expression. The total work done, concentrate here, total work done is given by P. Now is P is replaced by this expression K divided by V power of gamma between lower limit V1 and V2. So be careful here. So this expression P dV, just substitution, nothing else, right? So here, so total work done in an adiabatic process is obtained on integrating with appropriate limits, say V1 and V2. Here it is an adiabatic process, so adiabatic equation, this relation will have equation for P, K divided by V power of gamma. Now you just eliminate and substitute P value, right? Continue here. So P is expressed as K divided by V power of gamma. K is a constant, then put it outside, and then here, so V power of, take it to numerator, minus gamma dV. We can write 1 by x square, we can write it x power of minus 2 in a similar manner. So as we already know, integration standard formula like a plus b, a minus b whole square formula, always integral x power of n is always x power of n plus 1 by n plus 1. This formula you are familiar, we already discussed. So the work done in an adiabatic process K, now V power of, between lower limit V1 that continues anyway, V power of minus gamma plus 1 divided by minus gamma plus 1 between the limits, lower limit V1 and then upper limit, of course, V2. Just integration, nothing else. Now this minus gamma plus 1 is a constant, so the work done, so total work done in adiabatic process is given by K. Now this, I'll write it here, minus gamma plus 1, the denominator. And then substituting upper limit, that is V2 power minus gamma plus 1 minus V1 minus gamma plus 1. Isn't it? Just substitution, nothing else. Now total work done. Now I'll write K inside the bracket. I'll write it minus gamma plus 1 minus gamma. I'll put it this way. 1 minus gamma. K, I'll take it inside. K V2 power of minus gamma plus 1 minus, of course, K. This K, so they're expanding the bracket. V1 power of minus gamma plus 1. Student, just simple substitution, nothing else. Observe it carefully. Now K value, as we already written, so adiabatic process PV power of gamma is K, or P1 V1 power of gamma is equal to P2 V2 power of gamma. Using that expression here, 1 by 1 minus gamma. Now K, I'll write it as P2 V2 power of gamma. P2 V2 power of gamma. And then here V2, this adds this minus gamma plus 1 minus here K value, I'll write it P1 V1 power of gamma, P1 V1 power of gamma, and then V1 minus gamma plus 1. If bases are same, powers will be added up, isn't it? So now, I doubt whether it's visible clearly or not. I use this upper portion. Observe here, the total work done. So total work done in an adiabatic process, W. So continuation here. So it is 1 divided by 1 minus gamma. And then observe within the bracket, see here V2, if bases powers are added up. Base is same. So we have P2. So minus gamma plus gamma. On adding the powers gets cancelled. V2 power of 1. So P2 V2 minus P1 V1. A simple substitution, nothing else. Substitution and further simplify. Bases are same. Powers should be added up. Now, since we know for 1 mole of an ideal gas, 1 mole of ideal gas, we already familiar, PV is equal to RT, where R is gas constant, universal gas constant. So, using this expression, so for a temperature T1, P1 V1 is equal to RT1 and P2 V2 is equal to RT2. Now, substituting this data in the above expression, therefore work done is given by, so 1 by 1 minus gamma. So here P2 V2 is replaced by RT2 minus RT1, right? So finally, total work done, you just see here. So this, I'll revert these two terms, automatically these two terms get reversed, or take minus common and all those things. So finally, we can write R is a constant, take it out, common, gamma minus 1 within the bracket T1 minus T2. This is the work done in adiabatic process. I'll write here this work done, final expression, work done in an adiabatic process. In an adiabatic process. So W is given by, just here, final expression I have written here, R divided by gamma minus 1. So within the bracket, right? So T1 minus T2. Or you can write this entire expression together like this. Okay, so now you just not in an orderly manner, starting with work done in an adiabatic process. For a small change in the volume, small work done is given by PdV. In the previous chapter, we already learned and derived this, the work done by the system, right? In expanding the piston and all. If the volume changes from V1 to V2, then the total work done in an adiabatic process is obtained on integrating that above expression. So dW value is substituted here now with lower limit V1 and V2. Now, since adiabatic relation, because in an adiabatic process, the temperature does not remain constant. Remember, highlight, pressure changes, volume changes, temperature also changes. So we have to apply adiabatic relation. PV power of gamma is equal to K, or P is equal to K divided by V power of gamma. Now, substituting this information here in this expression here. See here, come back. So here, so this expression P is replaced. This P value, wherever P is there, replaced by K divided by V power of gamma. Now this taken to numerator V power of minus gamma dV. Now using this expression, x power of n is equal to x power of n plus 1 divided by n plus 1. So it's a familiar integration formula. So using that, K is a constant, you can put it outside the integration. V power of minus gamma plus 1 divided by minus gamma plus 1 with upper limit V2 and lower limit V1. Again, in the beginning itself, we discussed, so in adiabatic relation, PV power of gamma is K, or P1 V1 power of gamma is equal to P2 V2 power of gamma is a constant K. Now, expand this bracket K, take it inside the bracket. K value, just replace, substitute P2 V2 power of gamma and V2, and then here P1 V1 power of gamma. If bases are same, powers will be added up. Now finally, so on adding, if you want, I'll write one more step here, 1 minus gamma, here P2 V2 power of gamma minus gamma plus 1. Minus gamma plus 1 gets cancelled, so that V2 power of 1 you will get it. Here P1 V1 power of gamma minus gamma plus 1. So that minus gamma plus 1 you will get it. So P2 V2 power of 1, P1 V1 power of 1. The same thing I have written. If nothing is there, power is 1. When you are writing 2 means 2 power of 1. 3 means 3 power of 1. Here also P2 power of 1, V2 power of 1. But so for an ideal gas, 1 mole of an ideal gas, if you consider, right, PV is equal to RT. This is a familiar expression. You already studied this ideal gas equation. For 1 mole, PV is equal to RT. R is universal gas constant. Now, so P1, V1, when temperature changes, let us say in adiabatic process, all three of them, thermodynamic variables, pressure change, volume change, and temperature also changes. Let us say at T1, V1, P1 be the volume and pressure. Similarly, P2, V2 be the pressure and volume at temperature T2. Now, substituting this data, instead of P2, V2, let us substitute. So, P2, V2 is replaced by RT2. P1, V1 is replaced by RT1. R is a constant, take it outside. We have R divided by gamma minus 1 within the bracket T1 minus T2. This is the final expression for work done in adiabatic process I have written here. Right? Now, తెలుగులో చెప్పుకోవాలంటే ఇది సమోష్ణక ప్రక్రియలో జరిగినటువంటి పనికి సమీకరణం రాబట్టడానికి మనం గత చాప్టర్ లోనే మనం డిస్కస్ చేసుకున్నాం. సో ఉష్ణ గతిక శాస్త్ర మొదటి నియమం డిస్కస్ చేసుకున్నప్పుడు సో వ్యవస్థ చేసినటువంటి పనికి సమీకరణం ఆల్రెడీ ఉత్పన్నం చేశాము. dW ఈజ్ ఈక్వల్ టు PdV అనేది మనం ఆల్రెడీ గత చాప్టర్ లో మనం ఉత్పన్నం చేసుకున్నాం. ఒకవేళ ఘన పరిమాణం కనుక V1 నుంచి V2 కు మారినట్టయితే, వ్యవస్థ యొక్క ఘన పరిమాణం V1 నుండి V2 కు మారినట్టయితే, అప్పుడు ఈ ప్రక్రియలో అంటే సమోష్ణక ప్రక్రియలో జరిగినటువంటి మొత్తము పని సమీకరణం అవకలనం చేయాలి. అవధులు V1, V2 అవధుల మధ్య మనం అవకలనం చేస్తున్నట్టే మనకు మొత్తం పని వస్తుంది అనమాట. ఇక్కడ PdV సబ్స్టిట్యూట్ ఈక్వేషన్ 1 ప్రతిక్షేపించగా మొదటి సమీకరణాన్ని PdV టోటల్ వర్క్ డన్ ఆఫ్ కోర్స్ విత్ లిమిట్స్, లోవర్ లిమిట్ V1, అప్పర్ లిమిట్ V2. అయితే ఇక్కడ మనం ఇంతకు ముందు చాప్టర్ లో కూడా డిస్కస్ చేసుకున్నాం. స్థిర ఉష్ణోగ్రత ప్రక్రియ, సమ ఉష్ణక ప్రక్రియలో వ్యత్యాసం డిస్కస్ చేసుకున్నప్పుడు ఇక్కడ ఉష్ణోగ్రత కూడా మార్పు చెందుతుంది కాబట్టి ఇక్కడ సమోష్ణక ప్రక్రియలో ఉన్నటువంటి సమీకరణం PV పవర్ ఆఫ్ గామా ఈజ్ ఈక్వల్ టు K. సో గామా ఈజ్ అనేది 2 మోలార్ విశిష్టోష్ణాల మధ్య ఉన్నటువంటి నిష్పత్తి అన్నమాట. సో గామా అనేది రిలేషన్ బిట్వీన్ రేషియో Cp అండ్ Cp, మోలార్ సో విశిష్టోష్ణాల మధ్య ఉన్నటువంటి నిష్పత్తి అన్నమాట. సో ఈ ఈక్వేషన్ P బదులుగా మనం దీన్ని ప్రతిక్షేపిద్దాం ఇక్కడ. సో P బదులుగా K డివైడెడ్ బై V పవర్ ఆఫ్ గామా, దీన్ని లవం పైకి తీసుకెళ్తే V పవర్ ఆఫ్ మైనస్ గామా అవుతుంది. దీన్ని ఇంటిగ్రేషన్ చేయగా అవకలనం చేస్తానంటే ఈ సమీకరణం ఈ ఫార్ములా, ఈ సూత్రం అనుసరించి K V పవర్ ఆఫ్ మైనస్ గామా ప్లస్ 1 డివైడెడ్ బై మైనస్ గామా ప్లస్ 1 వస్తుంది అనమాట. ఫర్దర్ గా K సో అప్పర్ లిమిట్, లోవర్ లిమిట్ సబ్స్టిట్యూట్ చేసి సింప్లిఫై చేసిన తర్వాత ఫైనల్ గా మనకి ఏంటంటే K బదులుగా మనం P2 V2 పవర్ ఆఫ్ గామా, ఇక్కడ K బదులుగా P1 V1 పవర్ గా ప్రతిక్షేపించి మనం సింప్లిఫై చేస్తే కనుక ఫైనల్ గా మనకు 1 డివైడెడ్ బై 1 మైనస్ గామా విత్ ఇన్ ద బ్రాకెట్ P2 V2 మైనస్ P1 V1 వస్తుంది అనమాట. అయితే మనం సో ఆదర్శ వాయు సమీకరణం ఆల్రెడీ డిస్కస్ చేసుకున్నాము. ఆదర్శ వాయు సమీకరణం అనుసరించి PV ఈజ్ ఈక్వల్ టు RT. R అనేది సో స్థిరాంకం అనమాట, గ్యాస్ కాన్స్టెంట్. ఓకే, వాయు స్థిరాంకం అనమాట. సో T1 T2 ల వద్ద సో P1 V1 అనేవి సో T1 వద్ద ఉన్నటువంటి పీడనం ఘన పరిమాణం, అలాగే P2 V2 అనేది సో T2 ఉష్ణోగ్రత వద్ద ఉన్నటువంటి పీడనం ఘన పరిమాణం అయితే కనుక మనం P2 V2 బదులుగా RT2 అలాగే P1 V1 RT1 మనం ప్రతిక్షేపించి సింప్లిఫై చేసి R అనేది కామన్ మనం బయటికి తీసేస్తే మనం R divided by gamma minus 1 within the bracket T1 minus T2 వస్తుంది అనమాట. ఇది ఫైనల్ గా మన సమోష్ణక ప్రక్రియలో జరిగినటువంటి పనికి సమీకరణం అనమాట. సో స్టూడెంట్స్, మనకు ఇంతకు ముందు పార్ట్ లో మనం సో ఐసోథర్మల్ ప్రాసెస్ లో జరిగినట్టు పనికి సమీకరణం ఉత్పన్నం చేసుకున్నాం. ఇక్కడనేమో సో అడియాబాటిక్ ప్రాసెస్ అంటే సమోష్ణక ప్రక్రియలో జరిగినటువంటి పనికి సమీకరణాన్ని రాబట్టుకున్నాం అనమాట. సో hope you understood. So before that, so there are some processes: reversible process, quasi-static process, irreversible process. All these things you may get it for 2 marks. So they are important. Just let me introduce the terms reversible process. Reversible. What is a reversible process? Reversible process అంటే you just I'll give raw example. So ice తీసుకున్నాం. ఐస్ ను వెయిట్ చేసినప్పుడు ఏమవుతుంది? ఇప్పుడు వాటర్ ఫామ్ అవుతుంది. వాటర్ ను ఫర్దర్ గా మనం వెయిట్ చేస్తూ వెళ్ళాం అనుకో, వేపర్ ఫామ్ అవుతుంది. ఇక్కడ హీట్ చేస్తున్నాం, రైట్? దిస్ ఇస్ ఫార్వర్డ్ డైరెక్షన్ లో. సో ఆన్ హీటింగ్ ఐస్ it will melt, and then change of state will take place. It will melt, and then liquid state means water will be formed. Further you heat it, then vapor will be gaseous state. Vapor is formed. Reverse, you imagine on cooling, vapor on cooling gets condensed, water will be formed. Further you cool, again ice will be formed, isn't it? In refrigerators, if you put the containers will be there, you put some water and keep it in a deep freezer, and then so water will be converted into ice cubes, right? You are removing heat from water, you are cooling water, removing heat from it, then so water will be converted into so ice. That you will discuss a lot in the latent heat of fusion, latent heat of vaporization. There is a change of state will take place, right, at certain constant temperature and pressure. So anyway, it is a reversible process. The process that can be reversed back, retraced back, is called a reversible process. That's a suffusing of ice, vaporization of water, vapor. All these things are best example for reversible process. Irreversible process, that means the process that cannot be retraced back. It is called an irreversible process. So if you take a diffusion of the gases and all those things, right, then it is a irreversible process. The rusting of the materials and all those things. Okay, they are irreversible process. They cannot be retraced back. So they are irreversible process. Irreversible processes. The process that cannot be retraced back are called irreversible process. Diffusion of the gases and all those things. Okay. So now, what is a cyclic process? Cyclic process. That means in the beginning itself, the first chapter itself, we discuss in the introduction. So the system, thermodynamic system, so undergoes so changes at various stages, undergoes changes in various stages, and comes back to the initial stage. So say for example, so starting from A, and then here P1, V1, T1, then changes to P2, V2, and then T2 at point B, and then again so C, P3, V3, and then T3, and then comes back to starting point. Right? The system, after undergoing various stages, and returns back to initial stage, right? So here, when it is in a cyclic process, du will be equal to 0, right? So suppose the system doesn't come back to the initial stage after undergoing various changes, various stages, it doesn't come back. It is called non-cyclic processes. Cyclic processes, in fact, the heat engine is a wonderful example for cyclic process. Heat engine is a device that converts so heat energy into mechanical work in a cyclic process, through a cyclic process, right? The cycle keeps repeating at regular intervals of time. Thereby, so what happens? Heat energy will be converted into mechanical work, right? So here, the heat engine, even though it's deleted, but for competitive exam, it's very, very important. The efficiency of heat engine, the mechanical work done, heat drawn from the reservoir. Hot body, it will take heat from hot body, and then it does some mechanical work, some part of the energy, it will reject to the cold reservoir. So sink it is called. So the efficiency is given by this expression Q1 minus Q2 divided by Q1. This you can put it 1 minus Q2 by Q1, or this in terms of temperature 1 minus T2 by T1. This is efficiency of heat engine. Why? Because the thermodynamics, second law of thermodynamics. Just I have to introduce that. What is second law of thermodynamics? First law of thermodynamics. So it is a direct consequence of law of conservation of energy. Heat supplied is used to increase the internal energy and also to do the external work. This a reminder. So first law of thermodynamics says dQ is the increase in internal energy and the external work done by the system, isn't it? But first law of thermodynamics has some limitations. It didn't specify. Okay, it didn't specify so in which direction heat flows. So it didn't specify at all, and also it didn't explain the efficiency, the rate of efficiency with which the heat will be converted into mechanical work. Right? So second law of thermodynamics says so it is impossible to construct a heat engine with 100% efficiency. To put it in a simpler manner, second law of thermodynamics says it is impossible to design or to construct a heat engine having 100% efficiency. This is second law of thermodynamics. Second law of thermodynamics. So what does it say? It is impossible, means not possible to design or construct a heat engine with 100% efficiency. We have two different statements are there. So Kelvin-Planck statement and Clausius statement. Clausius statement, simple way, it is not possible to transmit heat from a body at lower temperature to body at higher temperature. But the reverse is possible. Higher temperature to lower temperature, easily you can transmit heat. It is impossible. It is not possible to transmit heat energy from a body at lower temperature to body at higher temperature without the external aid. This is second law of thermodynamics. It is not possible to construct a heat engine, so whose sole criteria, only result is to draw heat from hot reservoir and construct entire heat energy into mechanical work. It is not at all possible. This is second law of thermodynamics. Suppose you take this efficiency just now we discussed and derived is 1 minus T2 by T1. Suppose if you want n is equal to 1, that's 100% efficiency. If it is so possible, this T2 value should be 0. This T2 value should be become 0. But 0 Kelvin. But achieving absolute 0 Kelvin, that's minus 273 degrees centigrade, is not at all possible. So achieving 0 K, absolute 0 Kelvin, not possible. Therefore, so it is impossible to construct a heat engine with 100% efficiency. Now, one simple questions for your IP examination. So let me repeat, take it as assignment. So distinguish between isothermal and adiabatic processes. Note down, students, please note down the questions. Distinguish between assignment questions. Distinguish between isothermal and adiabatic process. Adiabatic. Distinguish between, note down, isothermal and adiabatic process. So isothermal and adiabatic అంటే స్థిర ఉష్ణోగ్రత ప్రక్రియ సమోష్ణక ప్రక్రియ మధ్యలోనే వ్యత్యాసాన్ని వివరించండి. అలాగే వర్క్ డన్, డిరైవ్ ఈక్వేషన్, వర్క్ డన్ ఇన్ isothermal process. అలాగే వర్క్ డన్ ఇన్ adiabatic process. అలాగే సో explain First law of thermodynamics. State and explain first law of thermodynamics. State and explain. State and explain. EXPLN means explain. First law of thermodynamics. ఉష్ణగతిక శాస్త్ర మొదటి నియమాన్ని తెలిపి వివరించండి. అలాగే ఇక్కడ సమ ఉష్ణక ప్రక్రియలో జరిగిన పనికి సమీకరణం రాబట్టండి. అలాగే స్థిర ఉష్ణోగ్రత ప్రక్రియలో జరిగిన పనికి సమీకరణం రాబట్టండి. అలాగే ఐసోథర్మల్ అడియాబాటిక్ ప్రాసెస్ మధ్య ఉండే వ్యత్యాసాన్ని వివరించండి. సో థ్యాంక్ యూ వెరీ మచ్ స్టూడెంట్స్. Hope you understood. If you want to compete with quality students, based on the knowledge you acquired, you have to work out as many numerical problems as possible. Thank you very much.